good evening and welcome to the second Better AI Meetup from Bratislava, Slovakia. It's actually the very first meetup in 2022, and hopefully it's the last meetup that we'll have as an online or almost online only, and the next time we'll see each other face to face, because I'm really missing the audience here. Today we'll be talking about big data and how to organize them for your AI projects, but first let me just say that this Better AI Meetup is a joint effort of HubHub, Innovatrics and Kinit. And we want to introduce you every time to one of the partners. Today it's HubHub, and HubHub is actually providing the space that you're seeing around me, and hopefully next time when you're here you will be seeing it. It's a network of co-working spaces across Visegrad 4 and the UK, but in reality it's much more than just a space. It builds an inclusive community focused on entrepreneurs, startups, scale-ups, corporates and institutions, and it's a collective of people with a shared goal to keep on growing. And HubHub is delighted to support and strengthen the AI community in partnership with Kinit and Innovatrics. So it's really a great fit for us, because what we are trying to build here is a strong AI community based in Bratislava and in cooperation with neighboring country. So as I mentioned, today we'll be talking about big data, and by big I mean really big, great, wonderful data. I'm almost speaking like Donald Trump now, but it's really about big data today. I'll be talking to Mr. Lukáš Csóka from Swiss Re Big Data Foundations, who is sitting right here next to me, and I'm really glad to have him here. But first, I'll introduce you to my colleague Marian Beszedes. He's head of research and development at Innovatrics. He'll show you how we organize our data in order to do efficient machine learning for our biometric algorithms. And if you have any questions, you can post them on Slido right now or later, and you can even vote for questions that you want to see answered. And I promise we'll try to answer as many questions as possible, as long as they are relevant to the topics that we are discussing. And let me introduce again Marian. Welcome.
Hi, Jonas. Nice to meet you. And hi to all who are looking at this presentation. Yes, thank you. So today I want to share with you our experience with processing of big data. We are dealing with machine learning with facial recognition. And we have found out that we must care about our datasets as much as for the code of our software. Okay, so, and I'm Marian Beszedes, and I'm a head of research and development here at Innovatrics. So Innovatrics is, probably you know it, it is an independent provider of biometric solutions. And we have many projects in more than 80 countries, more than 160 employees. And in our systems is enrolled more than 1 billion of enrollees. So this is quite interesting, even for me. And here in Brno, we are trying to develop biometric or libraries that are dealing with biometrics, and we have 3 biometrics modalities: fingers, irises, and faces. And today the most of the examples I will mention will be related to faces and data related to faces. So it's like 3 years ago when I first read these quotes by Andrew Karpathy, who is director of artificial intelligence and autopilot development at Tesla. And those quotes said that neural networks are not just another classifier. They represent a fundamental shift to a way how we write the software. They are software 2.0. And another quote that the gradient descent writes better code than we can do. So, and this somehow changed my mind and the way I was thinking about machine learning and datasets. So he used the term software 2.0. So first, let's say what is the software 1.0, and it is a way how we are writing the programs today or 10 years ago, that programmers define explicitly the behavior by deterministic handcrafted code and with some parameterizations of code, of course. And we all are familiar with it probably. It is there are programs written in C++ or Python, and there is more than 40 years of software engineering behind this topic, with a lot of methodologies like design patterns and unit tests and continuous integration, and plenty of tools, integrated development environments, debuggers, profilers, and so on. And what is software 2.0? So it's like it was mentioned in the quote, the optimization algorithms of machine learning compile the data set into a code that could be named as software 2.0. And there is not 40 years of software engineering. There is maybe 10 years or maybe 5 years. There are just few methodologies behind this topic. For example, data-centric development is one of them, and most of the things I will mention today are related to data-centric development. And for sure, there are no clear winning tools there, like special tools for debugging of machine learning algorithms, versioning of data, profilers, and so on. So before we go to some deeper thoughts about the software 2.0, let's explain when I mention data, what I mean behind the term. So in our case, data are images and labels. So in this case, you can see an image with many faces. This is just a single face image, and there are kind of boxes there, and these boxes are one of those annotations or labels. For example, here each face is annotated with this bounding box. There are some key points around the mouth and the eyes and nose and so on. And here you can see the segmentation of the face. You can have face description annotations like whether there are glasses, expression, mustache, and so on. You can have demographics like age, gender, race, or quality, whether those faces are blurred or sharp, or there are shadows in them, and so on. And these labels can be defined by humans or by algorithms automatically. So the first thing I want to mention is how we can store these data, because we found that this is quite important and difficult to choose the right solution. So at the beginning, we tried to store images just on the drives, and all those labels were stored in simple comma-separated values files, where each image has one line in that file, and you could easily compare these text files whether something changed or not. And it is human readable with just very simple editors like Notepad. But there were many minuses there. For example, structured data like those facial landmark positions, or for example, when you have many faces in one image, then you have to decompose the problem into two files, not just one. There should be annotations for images and labels. And when you have a data set with several millions of images, it could be complicated to store all those data just in flat files, uncompressed, without any possibilities of indexes or fast access. So we tried to find some solution for this, and what we have found is HDF5 format, which is maybe right, but it works for us. It is a hierarchical data format, and it is designed specifically for the scientific data. It has opened a model, a format, and library for storing and managing large and complex data. And the unit of this system is just a single file in which you can store data in a hierarchical form. And this file is easily portable. It has self-describing file format. There is no vendor lock-in, and you can keep your metadata together with the data. It is cross-platform tool. You can use it on any operating system. It has many bindings, and it has special features related to fast IOs. It has compression, encryption, and indexes, and so on. So it quite works for us. And we have two flavors of these special HDF files. One is just for the labels, for the annotations, and we can store there hierarchically the annotations for the images and for the faces. And we can store numerical or enumerated data types, or structured data like landmarks, or directly binary objects, like, for example, when we have a biometry, each face image can be represented as a template, which is good for the comparison. So also these templates can be stored there. And we can use the compression, which is built into the format. And from this label file, we can reference one or more image containers. And these image containers are very simple structure. Each image is represented as a binary object, and it is indexed by some unique ID. And these unique IDs are also mentioned in this label file, and that's the reference. And this is what works for us quite well. And what we learned is that HDF5 is good for the storing of numerical or array data. You can really easily transport or version these data files. Probably you know Pandas scientific library for the data operations, and Pandas has a native support for this file format. And good things is also that the HDF5 has many scientific languages bindings. So we can use it in Python or in R or also in Java. But there are also some cons that, so it is a binary format. So you can't easily view it. You need special viewer for that. You can't compare it to other HDF file. And there are some performance issues. We have found that once you open too many file descriptors, then the reading performance drops. So in our case, it is not optimal for the neural network trainings. We need to transform those data before the training in some different format. In our case, we use now TensorFlow records for the training. Okay, so we have a data format. Now we want to version those data. So, but first question, why would data change? What must happen to have a difference in your data set? And it is quite easy to have a change because everything changes in our world. So anyone can delete or modify image in the data set, and or modify some files even just with a text editor, or maybe we want to correct some labels, so we want to specifically change some information, or you could have a new algorithm for the annotation of the data, so you want to add some new labels to the data set, or there could be some existing annotations and you want to renew them because you have a new version of the algorithm, or the data file could just corrupt. Or you could have a data set that consists of a mixture of various data sets, and one of them could change or can be added. So all of these can lead to the change of data, and change of data will change your machine learning model, and you want to track it somehow. So in standard code, you could use Git for the version, and you can see who, when, and why change what lines of code. And in case of datasets, you also want to know who, when, and why changed your data, because your data write your code through the optimizers. And the quite difficult question is how to version code and terabytes of related data together. And in our case, we have a quite difficult way to find what is the right solution. So at the beginning, we didn't version anything but code, and we have found that it isn't the way, because you have no reproducibility. You couldn't find how we got those nice results we made just last week, because someone just accidentally changed some data and they were lost then. And or how to continue in a model version 2, how to continue development. And once you don't have the data that were the model version 1 trained, you simply can't. Or how to evaluate your new model on the previous testing data set on which was the version 1 model tested. So all of these questions couldn't be answered without versioning. So next kind of, let's say, versioning we tried to use was that we try to store all the data files on some remote storages, and they were the version was baked into the name of the dataset file, and the code has these dataset names versioned within the Git. And we tried to write these changelog files with all those tiny changes in the dataset, and it was really frustrating because all the time somebody forgot to write there something, so and it was unsustainable. It is very difficult to manually track all these changes, and those changes really happen. So we made another step to a better versioning, and Git has a feature of large file storage, and this is something really neat, because suddenly your big files can be stored or can be versioned as references in your Git, and the files itself can be stored in a special large file storage designed for Git. And there are some cons. You need a special large files storage servers, and this system doesn't have data science in mind. So we were there just a short time because we have found another solution, and it is called DVC, Data Version Control. It is a free open source tool. It is a command line tool, and it works very tightly on top of Git. And it is agnostic to storage type or programming language or machine learning framework. And it directly designed for the machine learning and for the reproducibility. And you can version within this system not just data, but also models or statistical results. And you can see it here. It is in some things, it is quite similar to the Git large file storage, because again, for each big file you want to version, you have a special .dvc file, which contains some abbreviation of the origin file, some hash of it, and some ID. And this DVC file is stored or versioned together with the code in a Git, and that big file is stored in so-called DVC remote storage, and you can choose which storage you want. There are plenty of them supported, and you use really similar syntax for both of these tools. So there's a git pull, git push, dvc pull, dvc push. So I have a coding class now here. So this is something probably all you know. So it is initialization of repository with making directory and initialization of the git, with committing the code for the training of some machine learning model and the code for data preparation. And now the DVC comes into game. So first you need to make a DVC init, and then you have to commit some configuration file related to DVC and some ignore files. And here is a command that copies the raw data into your repository. And this is the command which adds the data into DVC. It creates the .dvc file, which you need to commit into Git. And now this is how the file looks like. So there is an MD5 hash in that file, and the path to the real file. And here you can see that you could really easily add remote storage to your DVC. Again, you need to git commit the configuration, and now you can check whether all your big files are stored. And it says that there is one new file, so you can DVC push, and now everything is versioned. Okay, but DVC is much more. As I already mentioned, it is good for reproducibility, so it has pipelines, and these pipelines stores information how the datasets and models were built. So think about them as for the make files for the data for machine learning projects. And you can store into DVC not just the pipelines, but also some statistical metrics, parameters, or plots, which are good for the experiment comparison. So, and then suddenly you can think about DVC like about the Git for the machine learning. And the DVC itself is just the base stone for some more sophisticated tools written by iterative AI. Okay, so this is coding lesson number 2. So this is how you can create your DVC pipeline. This is a statement that create one stage of the pipelines and execute the command related to the pipeline. So here you can see the name of the pipeline, the definition of the dependencies, definition of the output, and the command itself. So so after you fire this command, so this statement will be executed, and this file and one more will be created. So the DVC-YAML file contains the definition of the stage. There's the command, the dependencies, and the output. And there's one more file called dvc.lock, which is quite similar, but the MD5 hashes of all the dependencies and outputs are stored there. So this is another creating of another stage, quite similar. So this is the machine learning training stage. So again, dependencies of the code of the training and the normalized data. Output is the machine learning model, and this is the statement. So afterwards, you can check the DVC deck. Deck stands for direct acyclic graph, which is the base paradigm for the pipelines in DVC. They must be DAX. And here you can see those two stages of the pipelines. Train stage depends on the prepared data. So if you write at this time just the DVC repro, nothing happens because all of nothing changed, none of the dependencies. So this statement makes some changes into the dependency of the prep data stage. So it changed the code, Python code. So, and now if I fire DVC repro command, it checks, DVC checks whether something changed. Yes, data prep py changed. So let's execute this stage again. And so the code wasn't changed. So the output of the stage data point h5 doesn't change. So the next stage of the pipeline won't be executed. So the pipelines define your execution process and helps you to execute just those things that are necessary. And this is nice. And here you can see some example of pipelines we use for the face annotation or facial data sets processing. So there is a stage for the raw data normalization. There is a dataset X. Then there is a data or face detection stage, some face quality annotations or age and gender annotation, and then you can merge everything together. And here you have a stage for some different data set. It is quite similar, but there is missing the gender annotation stage. Then you could have another data set which is very similar for the previous one, but there is a one more stage for invalidating of some records. And suddenly we have found that we have too many data sets, and we have a design feature that each dataset has its own repository, and each repository and its own Docker and Python environment and execution pipeline. So it means that all of these codes were repeating many times in different repositories. So we tried to remove this boilerplate code by designing our own Python package, which stands up on the DVC, and the code shares the stage definition for the commonly used stages. And of course, there are some stages that are quite specialized for those data sets. So, and these are just based on some base stages interfaces. So, and this is the way how we solve that. So, lessons learned with the DVC, it is really great tool. And it's great that it is file-based because files are everywhere and you can work with them quite naturally. And it has perfect community documentation and communication with the DVC team. Reproducibility is great. And I think that good design feature is that we have a repository for each dataset separately. Of course, there are some cons. So if you have many repositories, it is quite difficult to make some bulk changes to all dataset at once. It is file-based, so it is pro and it is cons at the same time, because sometimes you need to be dependent on some different kind of data, not just files. For example, data in SQL storage. They still didn't solve the problem with the parallel stages execution, and the tool for the garbage collection on the remote servers is not good enough. So these are the pros and cons of DVC. But software 2.0 is not just about the versioning. You can have some more tools for the annotation, data viewing, or for the data profiling or validation. So in the case of data annotation, it is not just the simple giving text labels that it is male or female, but you can draw your segmentations or your landmarks or bounding boxes. When you have such a tool, you want to validate the labels after some validators draw them, or you want to measure the performance of the annotators, or you want to maybe integrate your own machine learning model for the pre-annotation, or you want to hire some annotators through this tool. Everything of this is possible in this new software class. And we have experience mostly with software called Csóka Annotator, and it is the one that you could see here. But there are plenty of them, and here I mentioned just those that are open source, so try them. So when you have a lot of data, you need to view them quite fast. So for the reasons that we couldn't find viewer good enough for us, we tried to modify existing one. It is called vtables, and it is based upon the HDF file format and pytables library, which is binding for the HDF5 in Python. And suddenly we had a tool where we can sort the labels and filter them and compare multiple data files and make a visualization of some features we want to have, like bounding boxes or landmarks. So data viewing is one thing, but when you have a data set with 1 million of images, you couldn't simply check all of them. So you need some kind of profiler of the data or validators. So for this purpose, we use tool called TensorFlow Data Validation, and it can help you to find the problems with missing data or out of range values, wrong data types. It creates statistical schemas that can be validated against your own, let's say, perfect dataset scheme. And it can help you to identify anomalies in the data or find redundant or the most informative features or detect data drifts. So you can compare your data sets. And for example, in this case, you can see that this data set has records where the phase pitch angle is much wider than the other one. So it could be a data drift when you compare your test or train faults of data sets. There are more of these tools. Just two of them are mentioned here: SweetWiz or Data Prep. Each of them has different feature set. Some of them are nicer, some of them are smaller. So you have to choose them and select the best suits your needs. So lesson learned with these tools: there is no all-purpose, let's say, machine learning integrating development environment available. So you need to use combination of these specialized tools. So you have to choose the right one. And you can see, for example, the count of stars in GitHub for this purpose. But I think that better metric is the how active is the community behind that project, how many unresolved or resolved issues is there. For example, this is the pools view of the GitHub for the DVC project. And so you have to choose the right tool with the most stars, for example. Then you have to check whether it fills all your needs that you really need. And then don't hesitate to change it, to extend it or modify it if it doesn't have the feature you need. Okay, but all of these things I mentioned could or must lead to the better machine learning training reproducibility. So here you can see that this is the very typical machine learning pipeline, and all these things mentioned here can influence your results. So the data itself, all the code related with annotations, cleaning, and so on, how you split the data into train, valid, or test split. Then you have the training with the machine learning framework, data augmentations, hyperparameters, model attributes, and so on. And then you have an evaluation where you have to select the right metric, and you have the code the evaluation and the reporting tool. And of course, all of these are related to the versions of operating system, libraries, drivers, hardware environment, or Python environment. So all of these mentioned here can directly change the results you have as an outcome from your machine learning pipeline. So I think the answer to the question how to make the reproducibility is the versioning of almost anything. So you can version your code, configuration, metrics, or pipelines within Git. You can version your dataset in a tool such as DVC, or your models you can store there. You can version your environment using Docker. We can't live without Docker in this world of software today. So you can store there your Python environments or drivers. And of course, you have to version your execution, like pipeline executions, hyperparameters, or intermediate results of the pipelines. So, and all mentioned was related to one experiment. But imagine that you have hundreds of experiments and suddenly you lost where you are very easily. And you need a tool. And the tool nowadays is called Machine Learning Experiment Management System. And what does it mean? So you need to track your experiment metadata. I mentioned all of them. You want to provide your metadata for the collaboration in a meaningful way, and this is not mandatory, it is optional. It is really good when you have a tool for the organizing execution of your experiments in a deterministic way with a kind of scheduler. In our case, we have experience with the tool called ClearML, and you can do experiment logging, execution, scheduling, comparison, and it is framework agnostic. All you need is to add some reference to a Python package called ClearML and to initialize a task within it. And it has integration with a lot of machine learning frameworks. And this command is a kind of decorator which decorates or initializes decorators to all the statements of machine learning frameworks, and suddenly you don't have to write no more code, and the train command, for example, from scikit-learn will do logging into your ClearML experiment management server, where all the logs, metrics, artifacts, or models are logged. So look how does it looks like. So here you can see the list of experiments that were made, that some of them were aborted, some of them are still running. You can see how long does they run, how many iterations were made, or what was the result, or whether it failed with no result. Then you can compare experiment and compare what parameters changed, or whether the commit ID changed, or this is the change of hyperparameter. Then you can compare the training progress of two trainings. So here you can see that there is a different accuracy in gender classification, and you can choose your metrics you want to see, and you choose many experiments to compare, not just two. Here you can see the comparison of results. So this is the confidence or confusion metrics for the age estimation. So you can see that this model is quite better than the previous one, and this is the evaluation in the terms of mean absolute error of the estimated age. So, and when you want to add a new task to this ClearML experiment management platform, you need to fire this command where you specify the name of the project, name of the experiment. You need to specify the specific repo and the commit or the branch, which Docker image should be used, and which statement should be fired within this Docker, and to which queue should be this task enqueued. So those tasks are assigned to queues, and in this system you have workers which are assigned to these queues. So suddenly all tasks in one queues are consumed by a set of workers, and those workers can be on different computers. So very easily you can have a multi-computer machine learning platform, and you can manually reorder all these tasks. So some conclusions about ClearML. So the GUI is really nice and clear, and you can do some execution tweaks within it. You can reset, start, or abort the experiments execution. You can compare experiments. You can visualize the state of the queues or tasks, but of course it has some cons. The documentation is not as good as in the case of DVC. the scheduler of the task is really quite simple, and there is almost no dynamic resource management. So this is a new task for us to solve this problem related to machine learning operations, and probably Kubernetes will be the way how we solve it. And this is all from my side. So if you have some questions, I would be happy to answer them.
Thank you, Marian. Thank you for actually explaining what the magic, what you are actually doing, and what we at Innovatrics then use for powering our products. We already have some questions for from our audience. So I will start with the first question. Do you use HDF5 format also for archiving purposes, or just like work in progress format?
Mostly for the archiving, as I have mentioned. For example, for the purposes of trainings, it is not the best file format. Then we use the TensorFlow records because they are much faster for the multi-processing reading.
Okay. How are you choosing the tools that you use, or do you just just test or trial and error everything and just choose what you have? And a question that's tied to it: how difficult it is actually to switch tools if they don't work for you?
So first, it is a good idea to watch some blogs or watch some lectures related directly to this task. It is quite topic nowadays. So so just to find out what's on the table, then it is a good idea to check all those parameters I mentioned, like GitHub stars and the community activity and so on. And then just read the documentation and find whether all your really needed needs are fulfilled by these possibly chosen tools, and then you have to test them. So it's not easy, and so it's not easy to change the tool. So you really have to think twice before you do that. So
okay. Yeah, and last question, just a short one. How big are the datasets that you use? Are we talking about gigabytes, terabytes?
Okay, so the biggest datasets we have now are several terabytes. So this is in terms of images, and the labels have several hundreds of gigabytes.
Okay. We don't have any more questions, but if the audience has any more questions for Marian, he will be staying us until the end, and you can still ask the question. Just type that it's for Marian, and we'll get back to that after the interview. Thank you, Marian, so much for your presentation. Please stay with us, and I will be now talking to Mr. Lukáš Csóka from Swiss Re. I'm very glad to have him here in person. And
thank you for inviting me.
And you just heard that we have the largest data set is about terabytes. I'm assuming that that it's where you just only start. So we are talking about really big data with you. You work at Swiss Re, which is one of the largest reinsurance companies in the world, and we'll be talking about how you actually put the data to use, because I'm assuming that you're collecting lots of data every day.
The company is very old. It is 140 years of history, and for example, we are working now on one project which is not relevant about what it is. It's for actual reserving, and only the insurance guys around you, I think, know what it is. But the important thing is we are using 80 years of history of data, basically 80 years of development of the insurance contracts we signed and how they developed over time, to understand how we should reserve and how much money we should reserve for the contracts we are signing right now. So you can just see that the history that we have is already speaking about the volume, and then we are also using, obviously, as Innovatrics, lots of images, but in this case not faces and so on, but satellite pictures to understand the different risk hazards around the world. And they are also big, so they usually go in much higher volume. It can be up to hundreds of terabytes per project. And our central data lake has few exabytes.
Wow, so we are talking about really big data. So, I mean, you're obviously doing lots of research projects. How do they actually crop up in the company, and how many of such projects are you doing per year, let's say?
Yeah, that's a good question. So my team is quite small. It is together with me 11 people. So that's just small, but we are part of the central data science unit, which has around 60-70 data scientists at this moment, plus additional consultants, analytics managers, communications, and so on. And we do around 40 to 50 projects. And one good part about what we do is we are not focused on just one area. So compared to, for example, when you have a smaller company or smaller firms, or some even big companies, you have a team that does, for example, only predictive modeling or does only recommenders, and we do everything. So it starts with recommending systems to predictive models, to geospatial analytics, to anything else around. And it in the end always comes to us from the full company, and anybody within the company can come to us and tell us, I have an idea. And that's really good, because from many of these ideas there was development of lots of very interesting projects. And what also works, and what I will tell you, if you are, for example, a consultant in this industry, it's going to some teams or going to companies, do you have some ideas what we can do for you? That usually doesn't work. What really works with people to understand and get new projects is pull the, I don't know, accounting into one room and ask them, what are your pain points? What do you hate about what you do? And try to solve that. And that is usually when an interesting project can be solved. We are looking only at the project that can be solved by data. When it cannot be solved by data, we put it on other teams. And we can work on very interesting stuff across the company.
Yeah, I can fully see, you know, when you have like a room full of people and you ask them what do you hate about your work, that it really has to work nicely. You collect a lot of your own data. How many? Is it complicated to actually find data scientists? You are talking about tens of data scientists. Mostly, are they based only in Slovakia?
No. We have a global team. We have a chapters. One chapter is in Bratislava. That's the globally the biggest chapter, which is very interesting, and has around 20 data scientists. Then we have a chapter in Zurich, which is our headquarter. We have 2 chapters in in APEC, so Asia basically, and then teams, and obviously something in US. But getting and finding data scientists on market with some experience that understand, and that's one of the interview questions, so I hope if you are students you will now listen. I don't go into project with I want to use this model. I let the data choose the right model. So please remember that. Finding with these approaches and with some skill set is really hard and can take few months.
Yeah, so basically you are talking about, let's say, model agnostic people. You know, they are willing to try new things and everything.
Yeah, that's one of the questions I mainly ask. How do you select and which project you use in the project when you have a challenge on interviews? And the best answer, probably, or the very common answer, let's put it like that, is I know this model and it worked with me on this other project, and I would go with this. And if it doesn't work, I would go with this. And one of the a lot better answer is I build a pipeline. I make it in a way that I can just plug and play multiple models and just compare them and let the data choose, not let the data scientist, but really be I think data centric.
Yeah, so when we talk about this, can you give us some examples where you use like big data, ML, AI to actually, I don't know, design products, change products?
Yeah. One very interesting that will be, I think, quite tangible for people to understand is ensuring the delays of flights. In the past, when you wanted to buy an insurance for a flight delay, basically there needed to be underwriter that told for this flight we think this is the risk, so it's quite costly to have underwriter. When something happened, you need to push your claim that okay, something happened and I had flight delay of 4 hours and you needed to wait weeks till it was checked by some claims assessors. A really bad user experience. And one of the good part about data that we now know what are the flights. We know from the history how each company, how each flight, how each region, how each airport has the probability that it will be delayed. So you can create a flight delay system quite easily, connect it with the flight companies, and you can absolutely reduce the high management cost. And in this way, this is already big because you need to understand the flights around the world, and basically we cover 95% of flights, and it's complete change how we look at the insurance when you just pay few euros for a flight, and in the end, if your flight has a delay of 30 minutes before you are in your taxi at the airport, you have already the money, the claim processed, and on your bank account. And when you look at what is now opening around the world, what the insurance company, banking industry uses, they are trying to tap into any external data. They have lots of internal when they have a long history, and any external data. For example, very common in insurance is agrobusiness, agriculture, where you have satellite pictures, you have sensors, you have weather stations, and there are now companies selling that around the world. For example, thousands of weather stations that they have, thousands of IoTs, lots of the satellites for unbelievable amount of data, which was not processable in past easily. But with the technology, with let's put it like Spark, directly, with new approaches, with also the deep learning and machine learning options, now you can process and you can get lots of valuable insight. And one of the valuable insight can be that, okay, in past, again, farmer, there was a risk, so basically let's call it like earthquake happened, that's still probably not that much relevant to farmers, flood or drought or frost on the farm. And we needed to send a claims assessor to the farm to understand if something really happened there when he came to us. But now with this kind of information, the insurance companies and also VR that's providing us tools can directly, without sending somebody, provide the money even before it happens, because we can have also some predictive models on the weather, so we know that there will be frost. We can even tell the farmer that there is a high risk of frost, so they have the chance to prevent some of the damage. They use, it's very interesting, they use candles, really big candles on the farms, so to avoid the freezing. And so on. So this is, and when you want to use satellite data, it's always, you are always coming, when you are just looking at very small area, okay, you are speaking about gigabytes, but when you are looking about something like China, you are always coming just to terabytes, and when you are going to globally, it's hundreds of terabytes. So that's where you need to have your pipeline, and you need to be ready to process all this.
Yeah, I liked your example of the airline insurance, because it's almost like the perfect combination, that it's easier, it's faster, and it's cheaper. So you know, it's you usually get like, you can choose 2 of those. So this is really nice. Okay, so you collect obviously a huge amount and wide array of data. What tools or toolsets do you actually use to keep them organized, labeled? And
one thing we started already a few years ago is we are a big company. We have 15,000 employees around the world, and lots of departments, they are siloed and they are not speaking together. I hope just some our investors are not listening right now. So what we did is we need to have a central data lake, and that's where the fun starts. We cannot create a data swamp, just that we put everything as is into one place, but we need to have a proper place where we can put any kind of data, structured, unstructured. So it can be images, it can be text, it can be documents, it can be tables into one place. We need to manage the permissions, we need to manage the security in the right way, and then in the end, we need to be able to tap into this potential, because just having this data into one place, that's nice, but doesn't help you at all. So you need to be also able to catalog this data, and allowed the proper usage. So that's a little bit different compared to the data warehousing. The data lake versus data warehousing, there are lots of discussion, but basically data warehousing is for business analysts. You have the data really nicely structured, but in the data lake, it's really for data scientists and basically even anybody from the company. If you provide the right tools, you put the data as is. You need to have some governance on them. So you just cannot just put the data and anything that comes via email as Excel sheet, just put there. That doesn't work. That creates you data swamp, and after some time, you have there too much, and nobody understands, and everybody lost the. Nobody wants to use it anymore, and you created just data graveyard. But doing it in the right way is really hard. So what we went is we also went around the world at what other solutions are there. Basically, we have two solutions. One solution is called Foundry from company named Palantir. And second solution on some other projects is basically Databricks and the Azure ecosystem. And that are the main principles how we create our own data lake, where we have most of the data in one place. And that then it makes easy because then the data scientist or even many times the business and the data engineers and any kind of engineer can just go there, find what he needs, take it, use for the purpose. Obviously, you need to have some governance again, but when he gets the approval, he can use it.
Okay, so you mentioned the principles for your data lake. So, and I think that that's something that everybody kind of understands, especially if they are long in the business. They know about data silos and they want to put it all together, but they don't want to create a graveyard. So what should they do?
So one thing is you need to build it with purpose. Just going and building data lake because it's now really modern and everybody else around me does it, which is very common, is not right. It doesn't help you. You just spend the money and you have no benefit. So find the purpose why you need it. That's the first thing. Then you also need to find the right technology, also the right technical approach. Again, just putting everything on Hadoop, Hadoop can be and can become proper data lake, but that's not enough. You need to start with something which you get the benefit as fast as possible. But putting now all the data that your company has, I know you're a medium-sized company, 250 employees, and now for 5 years your engineering department just puts all the data into one data lake, but for 5 years you have no benefits. It's also not the right approach. You need to prioritize the sources that go there, and not everything goes there. And the last thing is the governance. You need to have the security, you need to understand who has access to what, and you need also to track what is in my data lake, so that when Joško from different departments wants to get access to some data source, he doesn't need to go to the database, he doesn't need to go to the people and every month, can you send me this Excel sheet from your accounting, as an example. He knows that it's there. And he can find it. So these are the main principles that you should, I think, guide yourself how to build a data lake. And let me put it like that: it's really hard. It's hard to do it properly. I would go with buying external solutions. There are Snow software. There are lots of companies that now are tapping into this industry. Based on Deloitte Insights in 2024. The full just the data lake industry, that's 24 billions of US dollars per year. So there already you can see there is big market. So there are lots of good options around the market, and just buy it.
Yeah, that actually sounds sensible, but I can imagine that it needs to go to a lot of trial and error before you arrive at the right solution. So
yeah. But usually you can get the trials from the companies. So you should use that.
So you mentioned before that you compare different machine learning models. How and why do you actually do it when searching for, let's say, optimum model for your solution?
So one thing, and that will be also very interesting, especially, and that's true really for banking and insurance. You have now regulators that understand what AI is, and want that you first make sure that it's what everything you produce goes according to the ethical principles. Also, you have again proper governance on that, and in the end makes sense. So, for example, doesn't discriminate anybody. That's one thing that you should really always make sure as a data scientist, as a person, as a human. The second thing is you should also care, and I care quite a lot about the performance, but just to be business sensible. I will explain what I mean by this. But first, I usually don't care about the models. I don't have any relationship with this model or this model. Many people come to us, are on interviews that I use for everything deep learning. That's quite nice, and it's good that you understand deep learning, but there are some easier options to use for lots of projects. You can get very similar precision, you can get a really similar performance. It's easier, and you can also make it more understandable and transparent to your business or to your client. So that's one of my point. And what we usually do is try to, for example, try 3, 4, 5 models that we think can work for data. Sometimes even 20. We had a case where we were predicting time series modeling, and basically we went a little bit overboard. We have there 20, 25 models at the same time running, but the benefit is there, so that was not the problem. So that's you take what is the best, and what is the best is chosen based on the data itself. And then why I care about performance and why I don't care about the performance. I care about performance because if you are just something around random, it doesn't make sense. The project should be stopped as soon as possible, and you should spend your time on something else, some other project. But also, what I see in many cases is the data scientists, especially for example, in the academic, spend years, and that's different compared to the commercial industry, but they spend years to build one model that is perfect for this data. In our case, I'm rather going with just 70% precision for 2 clients than just having 80% precision for 1 client. Because it's 2 clients happy is always better. So sometimes you need to see these diminishing returns and invest only as much time and as much resources as is needed to get to the good results, which is acceptable, usable, and it's basically even better than the industry, but you don't need to be perfect.
Yeah, you just need to be good enough.
Good enough.
Yeah, that's actually a nice approach. Have you also worked in some academic, let's say, research? So
not that much, that I could say. Not that much, but I saw it many times on papers that I tried to reproduce myself. When I was just going around the paper and how it was programmed, and I did the same or use, and I saw that okay, I need to execute it 20 times to get the same performance and you have, because it's really random and it's undeterministic, and that doesn't make sense. I want to have it right from the scratch, and I want to have a stable result.
Yeah, that's understandable. I wanted to also to get, because I mean part of your data lake is obviously a lots of documents, because I mean it's what you do. How do you use natural NLP and deep learning approaches? Are they useful for you in any way? And which languages are actually usable with NLP?
Yeah, okay, let me put it even before. When you are a data scientist and you will now solve the one of the biggest NLP problem, that the algorithms, the trainings of models is not data agnostic, it's not language agnostic, and when you solve it once, you will be a millionaire. Let's put it like that. The second thing, yes, we do. You can imagine the full insurance. We are an insurer, so it's not so bad. But the full insurance industry is in many cases paper-based. When you also look at banking industry in Africa, we work there. It's again lots of paper-based. So we have lots of solutions that we also develop internally to process these documents and process not just the documents as a text, but also extract the tables and so on. That's very one interesting factor, and we use 95% we use Python, and then we use some libraries that we produced or some open source libraries. That's probably the one thing. The second part was the deep learning. I don't like deep learning. I don't like deep learning because usually it's quite complex and you cannot easily explain what it does to business, to a person that has no no background. And you can explain something, but it's really intangible. So at any point when we can solve it by not using deep learning, I think that's the preferred way. So using the standard machine learning statistical methods. Obviously for text, you can use just deep learning, nothing else works.
Okay.
And there we use deep learning. I'm not the deep learning expert, but obviously we use all the standard models that are there. The biggest problem is the standard models, and everything works really nice and good for English, for German, for Spanish. Just it doesn't work with Indian language, it doesn't work with Chinese language, and then you have that's already 2 billion of people that you miss from your market. So you need to have solutions that works also with these languages.
Yeah, we actually at the first meetup we've been actually talking about the Slovak model. So, and do you have like any examples where the NLP can actually help or maybe automate, you know, the workings in companies? Because this is something that, you know, lots of especially financial companies are looking into, how to automate deals and everything.
Yes, for me it's for example, again, let's consider the insurance industry, because that is currently the closest to me. When you have a claim, when you write a claim as a person, you broke your leg, you have insurance. It's again written usually as a human, as a text, and you want to get your money as fast as possible. You don't want to wait. So one of the things we did is to automate. We cannot automate 100% of the claims for our insurance clients, but we can automate 30, 40, 50% of the claims. Depends on the industry, depends on market, depends on the country. And that helps quite a lot because you get the money faster, because when we automate it, then the decision is taken automatically for this percentage of the claims. And compare that you wait from the claim assessor for a week, 2 weeks, they could go on vacation, on some team meeting for 3 days, whatever else. So that's why it takes time. Now the machine tells you should get the money, and you get the money without the touch. So that's, I think, a good way how to use NLP, and it's a good way that the benefactor or the beneficiary of this is directly the people. That's what I like.
Yeah, that's understandable, and of course you cut a lot of the middlemen. So
yes, that as well.
They won't be happy. Okay, thank you so far. I'm not sure if we have any questions from the audience. Okay, not right now. In that case, thank you both, Lukáš and Marian. Maybe if Marian has some question from a data scientist to a data scientist, it's, you know, you can always take your time. But
do you hear me?
Yes.
Yes.
Okay, so I'm really curious how you use. So you mentioned those images, like satellite images.
Yes.
So what do you recognize on them? You mentioned them with relation to the agriculture.
Yes,
am I
a
right?
lot things. So we have lots of different line of businesses. It can be from that we want to understand wildfire, how the wildfire is spreading, so that we can offer, for example, inform even the local government, but also to understand where we will get the claim. That's very common, for example, wildfire risk in US. Then you want to, for example, understand where you have floods. That's really just common to Slovakia. We have lots of floods in Slovakia, quite a lot, and quite high risk around this. And when the flood is happening, we can use, for example, the satellite pictures that can usually that can go through the clouds, and we can understand the extent. And then we already know these properties, and we have the list of properties, and we understand where there are the properties. That you can buy this information. That's not so hard, and you can understand which properties were targeted. You understand which of these were your clients, and you can pay them out again faster because you know there was already something happening, and you can look at that as is happening. That's similar to farmer. You have the farmers, and compared to past when they needed to put the claims, and that's also is true for lots of the line of businesses and lots of the companies. Now all the companies should use the satellite, should use the weather stations, should use and go with different approaches to understand, okay, this kind of risks happened, this is what happened, we should pay out faster. So that's one of the. Obviously, we also do something else. In Brazil, in Brazil, it's a really high growing market. So the problem with high growing market is that you have farmers, that use very archaic methods and have quite low field, but at the same time expect quite low insurance commission that they pay. Then you have farmers, which are usually the bigger companies there, that are very close to what, for example, Slovakia's farmers are, really high yields, and that's the problem that they have. Then expect to pay. They are happy to pay more. They are even happy. The problem is that usually you don't have the insurance companies don't have the knowledge to set, and don't have also the people to set for each region, each farmer specific options. That these are your conditions, these are your conditions. So they sent one in the middle for everybody, which happens, which is bad, because then when you have the one that has high yield, he can even lose 50% of his yield and he gets nothing from the insurance, because it's something in middle and he's a lot higher. And when you have the lower, the payment for the insurance is too high for him. But how do you distinguish this is a farmer that is really performance and has high yield, and how do you distinguish between low yield? You ask them, I can tell you everybody will lie. Everybody wants to pay less for your insurance. Everybody will lie. You don't have a central registry for that. So what you can use is satellites. And you can look, for example, the last 5 years, you look at the crops as they were growing, so over the full period. So you need to, from the satellites, first understand where are the fields. You need to understand where was the harvesting, where was the sowing of the crops. And when you understand this period, regularly over the period, you check the farm. Obviously, you did for millions of farms at the same time. And you try to understand the yield. And how you understand the yield? This is a little bit of for example, this we found out from the academy. How can you understand the yield just from the satellite pictures? So there are lots of options. And that will help you to establish, okay, in this farm, the last 5 years we had this yield. So this should be the insurance. And we can now make insurance conditions specific for the farmer, which the farmer want. And that is the deal breaker from them, because they compare to have some generic insurance, they have something which is done specially for them.
Yeah, and I mean, you're mentioning like satellite data, but they are usually not just like typical photographs. I understand there's lots of different sensors, right?
Yes. So compare again to all the movies around the world. When you use satellites, most of the sensors on the satellites are not. It doesn't look at the world as you would look. That's called the true vision. They use different frequencies to catch, and they have different sensors to catch different frequencies. And some frequencies are very interesting, and let's put it like all frequencies are very interesting from specific physical needs. So when you have designer of the satellite, he knows which sensors to put there on which frequencies, because these are the one interesting. And for example, there is a combination of frequencies which, when you can understand, you understand, and you do a little bit of computation, you understand how much chlorophyll you have in the crops. When you understand how much chlorophyll you can crop, you understand how healthy the crop is. When you understand how healthy the crop is, you can understand how much yield the crop gives. So it is a pipeline of academic research, of decisions, but when you put it all together, you get into a new innovative product.
Okay, thank you. I think this is what everybody probably should take away from this Better AI meetup, that you have to put a lot of stuff together to actually make sense of the big data that you actually collect. So thank you, Lukáš. Thank you, Marian, for your attending, and thanks to everybody who was listening. If you have some more questions, please just write us back. We will be sending up a follow-up email with the links to this video, so you can rewatch it for the parts that you really liked. If you have any suggestions for the next meetup, please write us at better.ai.meetup@gmail.com. And we'll be seeing you on 23rd of March, which is right a month away from now. And hopefully we will all be here sitting in the auditorium. So thank you, guys. It's been a real pleasure.
Thank you for inviting me.
Thank you. Bye.
Have a nice evening.
Thank you. Bye.